All right.
Okay, hi everyone. I've just got a quick announcement and then I'll hand it over to Alad. So we've been a little inconsistent on the project deadlines. So here I'm clarifying it's going to be May 3rd at 11:59 p.m. That's a week from today. This is kind of a soft deadline. You can take more time if you want, but we figured, we didn't want to take up your RRR week necessarily, and we also want it so that most people will have something to talk about if we meet for project presentations next week. So I'll be, after class is over, I'll be like sending out something to collect interest on who wants to talk about what they did next week. And we'll go from there. So if you do need more time, don't worry about it. But our sort of optimistic deadline almost is May 3rd at 11:59 p.m. So with that, I'm going to hand it over to Alad. We are done with all the essential content. So this is just sort of a fun addition on, where computing is going to go next and some fun things to know about.
Hi, everyone. Does anyone have any questions before we get started about anything? All right. If there are no questions, Aditya, I don't think I can see the chat right now. Can you man the chat?
Yeah, I got it.
Okay, cool. So in today's lecture, I'm going to be talking about digital design, which is essentially the art of making rocks think. So people started out when we were trying to make computers. We started out with mechanical devices that didn't work very well, but they were very unreliable, very hard to design. Eventually, we moved on to systems of relays and systems of vacuum tubes to make switches, and using basically the central point of digital design is you control a switch with another switch. So we started doing that with electromechanical relays and vacuum tubes. And then eventually, at some point, I don't remember who exactly, but someone realized that if you put a couple pieces of silicon together, doped differently in different ways, you could make, or actually at the time it was germanium, you could make a switch that could be controlled by an electrical signal. So an electrical switch that can be controlled by an electrical signal. And ever since that day, we've basically, for the most part, been building computers and digital circuits out of funnily doped pieces of silicon or sometimes germanium, but usually silicon. So when you're thinking about these devices, there are both literally and figuratively many layers of abstraction that go into making these devices. And probably the most useful layer to start out when you're just learning how these devices work is actually one layer above transistors. And that layer is combinational logic gates. So what a combinational logic gate is it's not a single switch. It's a device that has, typically when you're just talking about things, it has two inputs and an output, or one input and an output. And it has a pretty basic truth table. So by a truth table, I mean these tables down here. So an OR gate does the kind of, it's an inclusive OR. So if A is a 1, so a large voltage, typically a high voltage, and B is a low voltage, a 0, and the output will still be a 1, a high voltage. If they're both 0, then you get an output that is a low voltage. And if they're both 1, then you still get an output that's a high voltage. So that truth table is summarized right here, where you have the input A, input B, 0, 0, you get a 1, 0, 0, you get a 0, 1, 0, you get a 1, 0, 1, you get a 1, and 1, 1, you get a 1, right? And these 4 logic gates are kind of the simplest to understand. And with them, you can build any logical operation. You can make an adder to add 2 numbers. You can make you can make circuits that take the Fourier transform of an input signal. You can do essentially of an input digital signal. you can perform any digital operation with these logic gates that can be performed by any other set of gates. There are actually typically, when this is taught, there's 4 more gates, which are the negation of each of these gates. So there's a buffer gate, which is just, it passes its input to the output. And then there's XNOR, NAND, and NOR. So there's typically an extra one, but I think these 4 are the ones that are easiest to think about. So then AND is just your typical, it is only true if A and B is true, right? Then it's a 1. Otherwise, it's false. Just to go over these. And XOR is my personal favorite logic gate. It is false if both inputs are false if both inputs are true, but true if exactly one of it. Sorry about that. That just crashed.
A quicker way of saying XOR might be 1 if they're different, 0 if they're the same.
Yeah. So XOR is basically what Aditya said. And I like XOR because it's very symmetric, and it has some neat properties that make it useful in a bunch of funny places you don't expect it to pop up. And it also forms the basis of a very simple adder. So if you add 0 and 0, you get a 0. If you add 1 and 0, you get a 1. If you add 0 and 1, you get a 1. And if you add 1 and 1, then your value in that place is going to be a 0, and then there's going to be a carry. So XOR is kind of like your really dumb 1-bit adder that overflows. And then the NOT gate just inverts its input. And this is the simplest logic gate, and we're gonna use it as an example later. Okay, the other half. Oh, sorry. So why do you care about these little logic gates? It's because you can perform computations with them. So the very basic single bit adder with proper carry input and proper carry output, right? So if you had 2 numbers that were multiple bits, right? So you have this number and this number, right? You could make, this is an adder circuit. We'll go over how it works in a second. But when I say it's a 1-bit adder, what I mean is that it takes that you have an instantiation of this circuit for this pair of bits. It takes them in, and then it has a carry output that goes to the carry input of the other instantiation of this adder for this set of bits, and so on and so forth. So basically, this is adding the way you learned in binary. Adding the way you learned to add in like 3rd grade, or whenever people learned to add in elementary school. I don't really remember. It was a while ago. But doing it in binary. So you have a carry chain that just kind of ripples forward, right? So here we see the XOR gate forms the basis of this structure. So if you have, if both of these are 1, then it's going to output a 0. Right? But if the carry input is also 1, then the sum bit here will be a 1. If the carry input is not a 1, then it'll be a 0, right? And if either of these are 1 and the carry input is 0, then we'll get a 1. If the carry input is 1 and one of these is if one and in one of these is a 1, you'll get a 0, and so on and so forth. It's kind of hard to trace out just like in your head how these work. But basically, if you'll take my word for it, and a lot of digital design is doing this, is someone designs something and you take their word for it that it works. Or if you sit down and trace this out, you'll figure out that this circuit up here does actually generate the correct sum. And this circuit down here generates the correct carry output. And then you can chain these together exactly like you would make, like basically if you had a bunch of 3rd graders and you had them each add 1 digit of a number and then pass the carry over to the 3rd grader to their right? This is the same thing, except you're doing it with logic gates. Another useful thing you might want to do with a computer is an if statement. So basically, if select is true, then I want to output whatever B is. And if select is not true, then I want to output whatever A is. This kind of if statement, but implemented with logic gates, is pretty simple to implement. Basically, you have an and here, right? So if select is 1, and then you have an or here. So if select is 1 and B is 1, then the and output from here will be 1, and the output will be 0. Or sorry, the output of the whole thing will be 1. If A is 1 and B is 0, then the output will be 0. And then we have an inverter here. So if the select is 1, then this will invert it and turn it into a 0 here. And you do the same thing with A. And then you just have an or to kind of combine those and reduce them. And you can use this structure and you can build it up into arbitrarily, like you can build a tree of these muxes, and then you can make if statements that have as many cases as you want, right? You can kind of see how that would work, where you just chain another mux out here, here, and you have a second select signal, right? So these are kind of just two examples of how you build stuff out of these gates. You can build stuff that is infinitely more complicated. You can make multipliers, which are very hard to make. You can build basically anything with these gates. And I just kind of wanted to show what some basic circuits would look like. And I'm going to post these notes. So if you want to try to figure out how this works, I very much encourage you to. It's a fun exercise to verify to yourself that this works. And I'll post a link to a really fun game where you design circuits this way and build up to a CPU. Okay. I know a couple of people in the class have already and tried that.
I'm not at all like circuits or digital design person, and I played it all the way through and loved it. So highly recommend. It's called NAND game, NAND game.
Yeah, it's a lot of fun. So the second part of any digital circuit in the modern world is sequential logic. And at your most basic, you really only have one type of device here, which is called the flip-flop. You have an input called D, an input called clock, and an output called Q. And the flip-flop is basically a storage device. So if the clock looks like this, it oscillates from, this is time goes up, right? So if the clock oscillates from false to true, false to true, false to true, right? What a flip-flop does is every time the clock has a positive edge, so every time the clock transitions from 0 to 1, right, it will read D, save it, and set the output Q to that result. So here before we've had a positive edge, and here, the output of Q is not well defined. But clock has a positive edge right here, and it sees that D is 1. So it'll take that value, store it in some magic internal buffer, which is actually usually two inverters chained together. A little bit of a cheat if you're playing that NAND game. You make this by basically having like a little latch here, right? So every time it goes to positive, it reads whatever D is, stores it internally, and sets Q to what it has stored. Then, as long as the clock is not transitioning on a positive, like doing a positive 0 to 1 transition, D can do whatever it wants. It can go 0, it can go back to 1, it can go to 0, it can go back to 1. The output of flip-flop doesn't care. It does not check the it does not resample D until the next positive edge. And here it sees that the output is 0, and it'll drop Q back down to a 0. And D can go back up to a positive edge again, and it can drop back down to 0. And at this positive edge, it'll say, okay, what is D? It's 0, so it's going to keep Q as 0. And it doesn't seem immediately obvious why you care about this flip-flop. Why not just have all your logic as gates, put them all in a line, and just have them compute your result? Like, why do I want to stop the computation and store the result at any point? And here's why you care. Here's the first reason. So say you have some logic over here, right? Like like this, it could multiply these two things, these two outputs, right? And you have some inputs over here, and they pass through some logic that happens that's only 1 or 2 gates deep down here. So some fast logic, and it'll happen really fast, right? And then they also pass through some slow logic that does some other computation on them that takes a while, right? Because these, our gates aren't perfect. They take a while for their inputs to propagate to their outputs. So if you have a bunch of gates really deep, it'll take a while. So what flip-flops let you do is they let you insert a synchronization boundary where you take these outputs and you have a clock that's running, and your clock period is longer than however long it takes for the slow logic to do its work. And this will, this basically inserts a synchronization boundary here, and it makes sure that these outputs Q to your next part of logic here, right, to your next little blob of logic, arrive at the same time, right? So, while this slow logic is doing its computation, this output could be doing it, it could just be jumping all over the place, right? And then the slow logic will finally arrive at its result, and it will jump to wherever it was, right? And you want to save that result and synchronize it with the fast logic. And this is synchronous logic. So you can design asynchronous chips where you try to use the delay of the logic gates intrinsically to synchronize everything and do everything, without some synchronization clock. And it turns out, people tried this, and it turns out it's nearly impossible to do. So flip-flops let you insert explicit synchronization barriers in your logic so that you can make sure that results are all arriving at the same time, right? Now, the other and perhaps more obviously useful purpose of this, obviously useful use of this flip-flop is to have feedback, right? So if you're designing a circuit, right, you might want some counter to count up, from 0, 1, 2, 3, 4, 5, et cetera, et cetera. And we're actually going to do this in a minute. Basically, what you can do is if you have feedback and you have some magic logic, if you have a flip-flop, you can add feedback to your circuit without it going so you can imagine if you had feedback without a flip-flop and you had a NOT gate and you connected it to its input, you can imagine how this could create problems, because every time this tries to output a 1, that's gonna go through here, and then this is gonna read a 1, and it's gonna try to output a 0, and it's gonna jump all over the place. It's gonna oscillate crazily. You typically don't want that. So this feedback, basically, if you have some blob logic down here that takes a number stored in these flip-flops and adds 1 to it, then on every clock cycle, you can now perform some operation like adding 1 and so every clock cycle, the counter will increase by 1, right? And this basic structure is the heart of every computer that's out there. Every general purpose computer has some counter inside of it. And what that counter does is it stores the address of an instruction. And on every clock cycle, it counts up by 1 or 4 or however long an instruction is, and it'll count up to compute the address of the next instruction. And the computer will fetch that instruction. And this basic loop is the essence of how we make computers that are actually useful. This is, if you look at the code from when we did the computer architecture section, you'll notice that I have something in there. There's a variable in there called a program counter, which does basically this, right? There's a while loop, and the program counter on each iteration of that while loop counts up, and that's this counter. And this kind of structure is really, really intrinsic to building any circuit that you might want to build. I noticed a DT popped up. Is there a question in the chat?
I know.
Okay, so we've just talked about logic gates and flip-flops. And I want to pause here and see if anyone has any questions. See if there's anything that kind of didn't really make sense, like why is this useful type of questions. I just want to address those really quickly. If anyone has those kind of questions. Okay, so so why is this useful? Basically, this is the essence of how we build computers. It's the essence of how we build, signal processing chips that you might use in physics. It's the essence of how we build, like, for example, on this summer, I'm going to be working on a particle detecting sensor. This is the essence of basically like how I get data out of our particle detection sensor, is through this discipline of digital logic and how you take digital inputs and you design a circuit that operates on them and then produces some output that you actually want. That digital logic is, like, in my opinion, in our modern society, this field is like one of the most important areas because so much of our society is driven by computation and so much of science is driven by computation. I think this is really important personally. And I really enjoy designing circuits too, which is because it's a lot of fun. You'll see if you play an AND game, it's a lot of fun. So I've told you that we can make these logic gates, right? Say we can make these. So how do we make these logic gates? One way to do it is to print out transistors onto a little wafer of silicon. So an example of an inverter would look like this. You have a PMOS transistor, right, that allows current through when the input is a 0 and does not allow current through when the input is a 1. And that PMOS transistor is connected to VDD on one end. So one leg of that transistor is connected to VDD, and one leg is connected to your output. When A is 1, this PMOS transistor will block current and won't let any current flow through this leg, right?
What does VDD stand for, or what does it mean?
Oh, sorry. VDD is the high voltage of your chip. So the logical one. So on a lot of chips these days, it's 1.8 volts, 3.3 volts. And down here we have ground, and that's 0 volts. So this is considered true, and this is considered false, right? 1 voltage stands for true, 1 voltage stands for false. Typically true is, some positive voltage these days, and false is 0 volts. There are some really old chips that kind of mess with this convention. Sometimes true is a negative voltage and false is 0 volts, but every circuit made in the last 20 years follows this convention pretty much. So down here we have an NMOS transistor, and it does the opposite. When its input is a 1, it'll allow current to flow, and when its input's a 0, it won't allow current to flow. So if you have A and your input is a 1, this transistor will be off, this transistor will be on, and it will allow current to flow to ground, which will set the voltage at the output to ground, right? If instead the input is a 0, then current can't flow through this transistor. This transistor will be off. The PMOS transistor will be on, and current, I don't know why I drew the no there, and current will flow through here, and it will pull the output up to a logical 1. Now, to actually make these on silicon, where is it? Here we go. So here's a picture of how these transistors are actually made. So on the left, we have a diffusion area. This is actually an N MOSFET, right? And the silicon substrate is doped with something. And then we have an insulating layer, and then a gate, which is made of another type of silicon, which is basically like small, tiny crystals of silicon that are grown in an oven. And this polysilicon conducts electricity, and if this is at a 1, then it will allow current to flow from the source to the drain. And if it's at a 0, it will not allow, if the voltage here is at ground, it will not allow current to flow from the source to the drain. And there's the opposite. A PMOS transistor has P minus diffusion here, P minus diffusion here, and N diffusion here on the rest of the bit. And it does the exact opposite. So if this is a 1, it will block current from flowing. And if it's a 0, it will allow current to flow from the source to the drain. The source to the drain, source and drain here are kind of historical terms because all of these transistors are actually symmetric, so there's no difference between the two. So when you print that out on a on an actual process, it looks kind of like this. So you have these 5-volt contacts, and then you have this diffusion layer here, and then you have this wire, which is the polysilicon, which controls the transistor, and then these two together will let current flow from this node to this node or not. So basically, this controls whether or not current can flow. This is a NAND gate, but it controls whether or not current can flow from here to here. So another wait, no, that's not what I wanted. Yeah, so looking at a cutaway, you can see kind of how it's actually built on the silicon. So you have the whole body of the silicon is typically doped lightly P minus. So you have these N transistors which have heavily doped regions, right? And then you dope a little bit of it N plus, and then you dope inside that big part that you dope N plus, you dope some more P minus or P plus. Okay. So this is an actual physical design for a transistor. So this is an actual physical inverter right here. And using this same technique, you can build arbitrarily complex gates. I'm not gonna go over exactly how to do that because they get really complex. So this, for example, this implements that adding circuit we talked about a bit ago. As you can see, it's a pretty complex circuit. Every time the red crosses a green or an orange, that's a transistor. So this has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 times 2 because each of these polysilicon crosses 2 areas. This has 28 transistors to implement that full adder. And it gets really complicated. And because it's so complicated, the companies who manufacture these silicon wafers put out these large libraries of they put out these libraries of cells that perform all the logic operations we talked about. So there's a 2-input AND gate. There's a 2-input XOR gate, and they developed 3-input gates. They developed adders, buffers, a bunch of different types of flip-flops, right? I don't know if here. Each of these, so they have a bunch of different types of flip-flops. And the flip-flops are they basically, these cells get really complicated, and you just you take what the manufacturer gives you, you trust that it works, you stamp it down on your chip. And I have an example of a chip. You stamp hundreds or thousands of these standard cells down on your chip. You wire them together with this blue and the purple that you see here. Those are metal wires. So you wire together all those standard cells with metal wires to make the circuit that you want, and then you end up with this obscenely complex chip. And the picture I'm showing you is an FPGA I designed. A class I was in designed last semester, and we're getting taped out. And this obscenely complex chip, that's like, this file is like 500 megabytes, and that's considered small, is much smaller than my fingernail, and it has ridiculous numbers of transistors. And this is on a really old process. These transistors are really big compared to the transistors that are in your phone or in your laptop.
Did you say what FPGA stands for or what it means?
I'm going to talk about FPGAs in a second. So what does this chip do? So this chip is what's called a field programmable gate array. That name doesn't really tell you anything about what it does, other than there's gates and there's an array of those gates, and it can be programmed in the field. So what does an FPGA actually look like? So basically, you build a programmable gate on an ASIC. So you build an ASIC. So sorry, I didn't ever define an ASIC. ASIC stands for Application Specific Integrated Circuit. It's a long, cumbrous name that basically means someone took a bunch of transistors and they plooped them out onto a silicon wafer, and it does the thing they want to do. So they build it. You build an integrated circuit that implements thousands and thousands of these programmable gates. And these programmable gates, right, take an input from some magic configuration box. They store the input from that magic configuration box inside a bunch of flip-flops, right? So that got stored inside a bunch of flip-flops. And then you have a whole load of wiring between a bunch of these magical programmable gates that, you know, takes input from some of those gates, and basically, like, you have A and B, and A and B and out are the wires in the circuit you designed for this chip. And there's a bunch of muxes that let you wire A, B, and out to other of these other programmable gates. And basically, A and B are used to select which of these bits gets stored in one of these flip-flops, gets passed to the output. So if I loaded this, these flip-flops, for example, if I loaded this one with a 0, I loaded this one with a 1, I loaded this one with a 1, and I loaded this one with a 0, then if A is true and B is true, then we'll get a 0 on the output. If A is true and B is false, then we'll get a 1 on the output. If A is false, right, so you can kind of follow, these are muxes here, right, and these select which one of these stored bits are go to the output. So if A is false, right, and B is true, so that will select this bit of here, that will select this bit here, you'll get a 1. And if they're both false, you get this branch, which is a 0. Now, I said a bunch of things, but basically the truth table for this is A, B, 0, 0, 0. So this is the truth table for this. And basically what we're doing here is we're making a programmable truth table out of another digital circuit. So we can simulate gates from a combination of other gates. Basically, it's like writing an emulator. We're simulating gates using other gates. So it's like you're writing an emulator for your computer, and you're running that emulator on your computer. And the emulator that you're running must necessarily probably have a bit less memory and be a lot slower, but you can change how your computer works without changing anything without, you know, going down and moving transistors around, which is very expensive. So different companies make these programmable gates, and they put thousands of them on a chip with a whole network to wire them together, however you may choose. And from there, you come up with your design, you throw it into some tools that they provide. Their tools are usually pretty bad, and your design goes on the chip. And with that chip, you are emulating basically what you would have implemented on an ASIC, right? So why do you, so you might ask, okay, we're gonna do a demo in a second. You might ask why you would want an FPGA if it's fundamentally slower than an ASIC. And the answer is, for a one-off, a cheap FPGA is $6. A cheap ASIC is $400,000. So if an ASIC is a tenth the price, or if an ASIC is a tenth the speed, but 100,000 times less expensive, if you can, sorry, if an ASIC is 10 times faster but 100,000 times more expensive, and you can put up with being 10 times slower, you probably want to make it on you probably want to make your device on an FPGA. So, for example, what is this used for? In one of the research projects I've been in for the past few years now, we have a box which has a very fast analog to digital converter. And that analog to digital converter outputs data so fast that we can't actually process it in real time using like any super fast server that's out there. And we can't interface it with it either. So what we do is we have an FPGA that sits between the analog to digital converter, analog to digital converter, something that takes an analog signal and converts to digital. And it reads the data from the analog to digital converter. And it's basically a very fast radio. And it performs some computations on it to reduce the data rate and extract the value that we care about. And then it ships that off to the computer. So that FPGA was about $2,000, and we can reprogram it on the fly. I can reprogram it, multiple times in a day with new circuitry that fixes a bug or implements some new processing, right? And I don't have to go pay a foundry $1 million and then wait 6 months for them to basically tape out a new integrated circuit that is custom designed by me. So it makes things a lot cheaper. And the reason that I think it's worth teaching about these FPGAs is, one, if you're just do it like designing instrumentation, they're really good for talking to any sensor you might have as fast as you need, and doing processing in situ next to that sensor without shipping your data off to a server farm. But also, if you have data in a server farm, it turns out that implementing a specific circuit to compute something in an FPGA is actually a lot faster. You can get a result a lot faster for certain types of computations than doing that computation in software on the computer itself. So I kind of think that in the future, as tools get better for designing programs for FPGAs, we'll start to see a world where a lot of supercomputers, instead of having GPUs, have FPGAs attached to them, where you design the circuit that performs the computation that you want and run it way faster than any CPU or GPU can run it. Because you can build specific circuits that are very finely tailored towards your application. And there's active research going on into making this possible and making this practical for large supercomputing. But that's what this class is about. And I think we're headed towards a future where FPGAs could play a big part in the most modern supercomputers in the world. So with that, we have a little demo. So first, I wanted to show you how you write a program for an FPGA or how you design an ASIC. So basically the most common language for specifying how you want one of these digital circuits to be laid out is called Verilog. And there exist things that are basically Verilog compilers, a lot like the Julia compiler, right? Because just like you don't want to write assembly when you're programming a computer, we discovered how painful that is. You don't want to individually tell the manufacturer how to wire every single gate on your circuit. So instead, you end up with a circuit description that looks like this. So here we have a module, and a module in Verilog is a lot like a function or a class, right? So it takes some inputs, it has some outputs, and it might have some internal state. So in this case, it takes an input, which is a clock. It takes an input, which is a reset signal, and it takes an input. It has an output, which is called count. And count is an 8-bit number. And inside, it has a register, so a flip-flop, basically, that is 8 bits wide. And it assigns the output counter to the contents of those 8 flip-flops, which make this 8-bit wide register, right? And then on every positive edge of the clock, what I want to do is set the internal counter, that internal register, to the previous value of the internal counter plus 1. Unless n reset, so it's the reason it is n reset is because I want to reset when reset is false. Unless reset is false, which means I want to reset, then in that case, I actually want to set the internal counter to 0. So Yosis is a tool which is nice enough to have an online, like a web interface that sort of works, and shows a graph of what it synthesizes. So at the most basic, I hit this before behavioral synth, and it shows kind of an abstract version of my code, right? So we have some equals block, which does this check here. We have an add block, which computes this addition here. And then there's some magic process here that it hasn't figured out how to exactly to implement. When I implement that, when I take that and I tell it to synthesize it into behavioral things, so flip-flops, adders, muxes, right? It says, okay, there's going to be a mux here with a select that comes from the check, does n reset equals 0, right? So if n reset equals 0, then this mux will select this. Oh, I should actually zoom in here. Sorry. This mux will select either 0 or the old value of internal counter plus 1, which is what this add block does. And the mux will select either 0 or that, depending on the value of reset. And on the next clock cycle, the flip-flop will get set to either its old value plus 1 or 0, depending on whether or not it was reset. And then internal counter goes to count, which is output, right? And I can even ask Yosis to synthesize this into logic gates at the most basic level. Whoops. And if I do that, I get the following very large graph, which has taken those adders and transformed them into just logic gates. It's made some adders out of XOR gates down here and some AND gates here to handle the carry. We have the mux, which has been transformed into 8 individual muxes for each of the bits. And we have the flip-flop, which has been expanded into one flip-flop for each bit, right? I noticed there's some stuff in the chat, Aditya.
No, it was just us shaming you for your spelling of programming.
Oh.
That was why I was laughing, because you spelled it programmable.
Okay.
It was funny.
So this is how one of these files gets synthesized. So you can see how these files get synthesized into logic. So okay, so over here I have nearly exactly the same thing. And this is a file with exactly the same stuff, except I've increased the size of the counter to 30 bits. And I have a little bit of wrapper code up here, which we'll see what it does in a second, but mostly just focus on all the functionalities in here. And what I've done is next to me, I have an FPGA.
Can you on-screen share for a second so everyone sees it full screen?
Yeah, so next to me, I have an FPGA board right here as attached to my computer.
Maybe try to pick a piece of paper over the LED.
So going back to screen sharing, so what this does is I've told my computer to go ahead and turn that into, so each of these little boxes is one of those programmable gates we talked about. So I've told my computer to go ahead and transform that design I had that I just showed you into a bunch of programmable gates and programs for those programmable gates, and then wire them all together and wire different pieces to the output pins of this FPGA chip, right? And what I'm going to show you in a second, Aditya, do you think you could spotlight my phone?
Yep.
Okay. Okay, so sorry, could you turn the light on? Okay, so here's this chip, and right now I have a pretty non-assuming program loaded, right? So you can see there's no activity on these LEDs. If I go onto my computer and I tell it to load the program that I just showed you, it will do that after a few seconds. And you should see now the LEDs counting up. So can you guys see that?
Yep, we see it.
Yeah, so you can see those LEDs counting up. And this doesn't seem that actually that interesting, but these are the highest bits of a 30-bit counter. And that 30-bit counter is counting at 12 megahertz. And the only reason it's counting at 12 megahertz is that that happens to be the clock I have set up right now. This program I wrote can easily run up to more than 200 megahertz, and you're only seeing the highest 8 bits. So if you divide 12 megahertz by 2 to the like 22 or something, you'll get the frequency that that lowest bit is flashing at, right? And we can, of course, if I go back and I screen share.
Yeah, that's about 3 hertz, which seems about right.
Yeah, if I go back on a screen share and I change the bits that I map to the LEDs and my little piece of wrapper code to be from 22 to, can someone subtract 22, 5, 15? I think that's 8. There are 8 bits there, okay. And I program, if I reprogram the FPGA, and Aditya, if you spotlight my phone again. Oh, it is spotlighted.
Yeah, spotlight's still on.
You can see that now I've switched to the lower bits, the counter is running much faster, and actually the lowest bits flip so fast you can't even see them, right? Yeah, so that's all I have for this demo today. I recommend you go play NAND game. These FPGAs are really cool. So for example, what I have set up right here is this is a little RAM module. And this FPGA is actually large enough I can implement an entire CPU on board here and have it run and boot Linux, a very stripped down version of like the full Linux operating system, what I'm running on my computer, on the CPU I designed for this, on a CPU that you can design for this FPGA. And personally, I think that's a lot of fun. So you get to try out custom designed CPUs that you wrote yourself, run code on them. The program I had before I programmed the latest, the program that's flashing these LEDs real fast, was a CPU I designed that was just running a basic, LED blinking program. Yeah. So I think these are a lot of fun. There are fairly cheap ones. If you look at the ICE 40, I can post a link to a couple of cheap FPGAs if this seems like something that's cool, and some resources to learn this stuff if anyone's interested. But that's all I got for today. And I'm just going to hang around for a bit with Aditya if anyone has any questions. Thank you all for joining us this semester. I had a lot of fun teaching this class, and I know Aditya did too. I'll let him talk about that.
Yeah, thanks a lot to everyone, and hopefully see you next week for project presentations. Really excited to see what y'all have made or will have made. I'm guessing it's all going to be done in the weekend right before, because we are all undergrads.